Can everyone hear me? Excellent. All right, so how many of you have actually read the Satoshi white paper? Okay, that's good. It's a brilliant paper, but as we've discovered in the last several years, it's got a few serious limitations that we think can be fixed, but they present some serious challenges, especially for scaling. Amongst these, it was really built as a single code base, which was meant to be run in its entirety on all machines, and all machines were going to participate equally in this peer-to-peer network. So in a homogeneous network, every single node pretty much runs the same software. It pretty much offers the same services, and this isn't really how the internet works. We have other kinds of devices that don't necessarily have the same capabilities as others, and in general, we have a very heterogeneous network. And different devices have very different capabilities. So for instance, a handheld device that has intermittent internet access is probably not the best place to do mining. Similarly, a very large server in some data center is probably not the best place to do point-of-sale authorization. So this was really something that was thought about, like there's like almost like, like a footnote in the, there's a section in the white paper covering these kinds of use cases, but it wasn't really the use cases that were really, fully thought out in the white paper originally. So then, of course, this is an infamous one. Pooled mining was not really accounted for. Once you get mining pools into the picture, a very, very large number of nodes now no longer participate equally in the selection of which transactions go into blocks, creating points of centralization and making it possible for people to maybe start censoring stuff or form cartels or whatever. And then also it amplifies errors. If any of these miners, if any of these mining pool operators is running faulty software or has some other issue, that really quickly gets amplified. Whereas with the other, homogeneous network, really, if someone decides to run some software that's like unconventional, they're probably not going to screw up the rest of the network. Then on top of that, we have pressure of centralization, where mining pools and miners have an interest in reducing latency as much as possible, which creates pressure to try to put all this equipment in one location, or try to make it so that they have special connections to each other that are no longer the peer-to-peer links that are in the homogeneous network. And of course, one CPU, one vote. We all know that in the original white paper, the idea was that people would want to use their CPUs for honest reasons rather than trying to subvert the network because it was more profitable. But as we found out, it turns out that specialized hardware is much better at actually mining. So most of the CPUs now are not being used for that, and there's incentives still for using CPU power for other kinds of attacks on the network. And then, of course, there's simplified payment verification, which was kind of like a last-minute idea. As it appears on the paper to be kind of like a last-minute idea. How are we going to deal with this situation where most devices are not mining anymore? So the idea was, to have kind of like a client-server architecture in a sense, where the servers are all part of miners, and clients basically get short proofs that their transactions are valid in a way that is cheap to verify on relatively small devices. There's a few problems with this. One of the things that is commented is, there's certain things that we just cannot verify using SPV. For instance, we cannot fully verify that blocks are actually valid. We cannot verify any transactions that we did not ask for. And we cannot verify other things that would be really relevant to wallets. For instance, whether a transaction has been spent or an output has been spent or not. We can prove it's been spent by demonstrating if there's a spend proof, but there's no unspent proof. So we need better cryptographic commitment structures to be able to accomplish these kinds of things. Where we really want to be able to prove these things, construct very short, efficient proofs, and make it possible to to have small devices actually participate in the network and not have to trust anyone. So Bitcoin has a global state, you can call it that, where you basically, it's the longest chain. Everyone agrees on what the history is. And then, specific systems might have a smaller view into that of what they're particularly interested in. So a cryptographic commitment structure allows you to verify what's yours without having to necessarily download everything else from everyone else. Generally has a root hash, which allows you to compare two different states. So I know for sure that my state is the same as someone else's, even if their view of the state is different from mine. One of the key features of Bitcoin is permissionless updates. Anyone can broadcast a transaction. Any miner can try to mine a block. You don't need to have any kind of special keys or anything. You don't need to have any passwords, or you don't need to do anything like that to actually enter anything into the blockchain. And this is a key feature of blockchains. This is actually one of the things that makes them most useful. It makes them censorship resistant, and if you remove this property, really what you end up is with a really inefficient database. So this is key. And then you need to be able to make sure that that what you actually have is correct and follows the rules of the protocol, follows the consensus rules. The key tool that we use for this is Merkle trees. Merkle trees allow you to verify the state of the system without necessarily having to have all the data. You can just have the pieces that you want, a little bit of extra just to be able to construct the hashes, and with that you're able to verify. And this is a logarithmic scaling thing. In the Satoshi simplified payment verification, every single block contains a root hash for transactions in that block, and you can just, here the yellow dots represent your own transactions that you're interested in, and you're able to make, the SPV proofs are able to demonstrate that that transaction is in fact in that block. However, you're not able to prove that a transaction is not in a block, or that someone withheld that transaction from you if you queried for it, along with all the other stuff I said that you cannot prove. So this is a really big problem. Another big problem with this approach is that you really need to scan the whole blockchain to be able to know when the first transaction occurred. I want to know the first time that this output got paid. There really is no way to quickly query a node and say, what's the first block that I need to download? You need to basically go, all the way to the beginning and ask for these proofs. So there's structure inefficiencies, and then there's certain things that we just cannot prove. There's this whole architecture difference in the change in topology, which was not really accounted for. I mean, it's something that's doable. It's not something that is impossible to do, but really the original white paper doesn't really consider other kinds of network architectures and topologies other than just a peer-to-peer mesh network, a homogeneous peer-to-peer mesh network. And there's also a huge privacy issue. If you're querying something from other machines, those other machines are going to know what you're interested in. So you might be revealing private information in doing that. And then there's this huge issue which I think has been very, very much, it hasn't been spoken enough about in this space, is incentives. Really, right now, we're relying to a large extent on altruism, or on nodes that basically have indirect incentives to run full validation nodes that can provide these proofs to other nodes in order to be able to keep the network in operation. But I think one of the things that really made Bitcoin succeed in the beginning was that the incentives were properly aligned. People had an incentive to actually run nodes, and that grew the network. That grew the size of the network considerably. It wasn't that you could use Bitcoin at retailers, or you could trade them on exchanges. That came later. The reason that Bitcoin was successful in the beginning was because you got paid for contributing resources to the network. And this is something that I think we really need to revive if we want this to grow and become worldwide. Because that's really something that we have over any other payment processors, Visa or whatever. No matter how hard they try, they're not going to get people to just voluntarily want to donate their computers to their network. Bitcoin did do that. And this is the magic of Bitcoin. So we need to fix the incentives. So As far as commitment structures, there's several different ideas that have been proposed as far as how we can improve that. There's a lot of different trade-offs. I think a lot of these trade-offs are relatively small compared to, doing it versus not doing it. This is something that we can discuss later on as far as figuring out what the best commitment structures really are. But for instance, one example is radix trees, where this allows you to quickly query for any particular piece of data that you want, because the actual data itself is the key. So this would allow you, for instance, to query for transaction outputs that you're interested in and still be able to verify by combining this idea with the Merkle tree idea. Right? So here you would still combine the hashes in the same way as a Merkle tree, and this would allow you to effectively make sure that all the transaction outputs that you're interested in, or any other kinds of data that you really want to query, you can actually quickly access and see that they are in fact part of the whole global structure. With this kind of idea, we could do what some have called flipping the chain, which basically means that you can query for your transaction outputs, you can query for the committed state that you're interested in, and make sure that these actually are part of the blockchain. And this way it would allow you to have much more efficient queries, and would allow you to actually be able to prove much more than you are able to do with what we have right now. Then you might not necessarily want to verify everything all the time. Not every node needs to verify everything, so there's certain things that we can do to at least make it possible to verify, to do some sanity checks on blocks. Among these, we can check limits. So we can make sure that it doesn't exceed the maximum block size, that we don't have more op counts than are allowed. There's conservation laws that we need to enforce, so we don't want Bitcoins being created out of nowhere that are not block rewards nor fees. We definitely want to make sure that the coins that are being spent actually exist and haven't been spent before. And we need to make sure that obviously the crypto stuff works out, that transactions are properly signed, etc. So all these things could be checked individually if we had commitment structures that allowed it. Another tool that we could use, and this tool could be used for some of those things that I just showed, is sum trees. So this allows you to verify that the total, for instance, of all the inputs or all the outputs of a block total to a particular number without having to have all of them locally. You can just check your particular outputs and make sure that they are actually included in that structure without having to download the entire structure. The second thing is we don't really have good query mechanisms for the SPV stuff. Right now we have a mechanism where we can use filters. You can use Bloom filters to ask other nodes to give us filtered blocks. However, this introduces the whole client-server architecture again. We really have no solid model for how to approach this. So here, obviously, if you make a query with personal info as far as like what you're interested in, other people are going to know a little bit about you. You might not want to reveal so much about yourself. With Bloom filters, there's an inherent trade-off. You can have a lot of privacy in one extreme, which basically means you download everything. And on the other extreme, you just download what you're interested in, but then the other node knows what you're interested in. So Bloom filters have a false positive rate, which makes it so that they're a little bit more private in the sense that some of the transactions that you're going to be fed, you might actually not care about. But this has several significant weaknesses that have been discovered, and I can't really get into them too much right now, but there's basically a trade-off that this is something that we haven't been able to find a way around yet. One idea that has come up that could possibly solve it is to commit to the Bloom filters in the blocks. So then when you download a block, you can check to see whether there are any transactions that are of interest to you in that block, and then you can go query for those transactions, not necessarily from the same peer. So you could query transactions from a whole bunch of different peers. Hopefully they're not going to collude against you. That would give you a little bit more privacy. And then the big one, incentives. Right now, verifiers, they have an incentive to make sure that they're not getting ripped off. However, a lot of people don't want to run a full node. they're going to be trusting other people to verify stuff for them a lot of times. That is not the desirable situation. We would like everyone to be able to verify everything for themselves. As for provers, really right now, as I said before, we're relying a lot on altruism or on people who have indirect incentives to run machines to keep the network in operation. They're not getting paid for this. And this is something that's a really serious problem, because as this number of nodes is reduced, the smaller it gets, the more prone to censorship the network gets, the more centralization there is, and the more single points of failure there might be in the system. And so this is a really huge problem that needs to be addressed. This is something that I believe will be possible to start addressing possibly with off-chain micropayments, where you're able to have ways of querying stuff and actually paying small amounts in efficient ways to be able to get that data and to incentivize people to actually run the provers, the nodes that actually construct these SPV proofs. So one of the things I think in Bitcoin really is fundamental is fixing the economic incentives. I think if we're able to make it so that these things are reasonable and people are willing to do this because they are directly rewarded, almost all the other problems will fix themselves. A lot of the things that we're talking about now, especially at this conference, are really things that are looking to get around obstacles that are caused because the incentives are skewed, because we don't have the proper incentives, so we need to artificially create them. But then if we create artificial incentives and we externalize things and there's no real accounting for who's contributing what, that means that we're going to keep on having to add hack after hack after hack, and it really kills the incentive for people to grow the network organically, in a decentralized fashion. And I think that that's really the key thing that could lead to Bitcoin going mainstream. So it needs to be cheap to cooperate, expensive to attack. There needs to be a way to offer resources, say, hey, I'm a node, I can do this for you. You want to do this, and have a way for those that want those services to find the nodes that offer those services, and a way to possibly pay them through micropayments. There really shouldn't be a need for everyone to validate absolutely everything. Full validators right now are validating everything. This is something that probably will not scale. We're going to have to find a way to either shard this, or either have partial checks with some probabilistic scheme, or something that we're going to have to sacrifice something in order to make it possible for there to be millions of thousands and thousands of transactions a second happening all the time. Because right now it's not a matter so much of resources that no computer in the world can do it. It's just nobody wants to nobody wants to be the one that's there's a tragedy of the commons element. As long as there's one whistleblower, one person on the network that's actually an honest node, sure, the network could in principle work, but who's going to do that, right? And the fewer there are, we run into the problems we already talked about. Then another interesting thing is it's possible to either spread the risk or delegate it and have other people watch the blockchain for you and alert you when things happen that you're interested in. These mechanisms are something that are currently being worked on, and I think this has a lot of promise. This means that you can have a small device. You don't have to be looking at everything all the time. If you can do this in a decentralized, trustless way, I think this solves a lot of problems. And finally, we need scalable commitment structures. We need a way to have a consensus layer that can verify global transactions in a way that's easy to locally verify. And this is something that really needs a lot of work. I would like to see a lot more attention put into this. I think that this is, if we're going to talk about scalability, this is probably where there's the most gains to be had of all the things that we've talked about. So I'd be happy to answer any questions for you. I am accessible online if you want to know if you want to have any links or any other information about what I've talked about. I'd be more than happy to talk to you. I'll be here for the rest of the conference. So thank you very much.